Picking up with problem number 11. Assume that a procedure yields a binomial distribution with n equals 6 trials and a probability of success of p equals 0.6. Use a binomial probability table to find the probability that the number of successes x is exactly 3. Alright, so we need to use the table. We can click up here and it'll bring the table up. Or you could look in the back of your online book and it should be there. This table can actually be used to work a lot of binomial probability problems, even if it doesn't tell you to use the table. There are a couple or some that you can use it on. And the way you use this table, it says n equals 6. So you look over here to where n equals 6 is right there. And then p equals 0.6. The p is up here at the top. So there's the column for 0.6. And there's 6. Now we're looking for the probability of 3. Exactly 3. So under 6, you go to 3 as your random variable. And then over to p equals 0.6. Again, 6 is the n, the x is 3, the p is 0.6. So that would be 0.276. There it is right there in the table. Alright, this next problem here, you can actually use the table again. There's two ways that you could do it. You could work this out using the table. If the table has a p of 0.75, that's the only thing. I don't think that this table is given. And it doesn't even have a link for the table. But you could find the table in the back of your textbook if you needed that. Here it is right here. The only problem is we don't have p equals 0.75, so we would have to estimate our answer, which isn't good. We don't want an estimate. But if our p was equal to any of these and it was a binomial distribution or a binomial probability problem, then we could use this table. I believe that this problem actually tells you, though, to use the probability formula, the binomial probability formula. So that is in your textbook. You need that. It should also be on your formula sheet. I pull the formula sheet up. I usually go to the website, but you can use the book. Either one is fine. You kind of have to search through to find it on your formula sheet in the book. But you know, here it is right here. It's pretty small. If we scroll down a little bit, you see a binomial probability formula here. Again, it is in your textbook, and so it's not too hard to remember too if you wanted to. But if you're not majoring in math or something like that, you probably wouldn't want to take the time to remember the formula. But it's n factorial over n minus x factorial times x factorial times p to the x times q to the n minus x. Alright, so let's go back to our problem. We're given that n equals 5, x equals 3, and p equals 0.75. So we want to use that formula. So plug in your n, so that'll be 5 factorial over, we have n minus x, so 5 minus 3 factorial times x factorial, so that's going to be times 3 factorial. And then we have p, which is 0.75, to the x power. Our x was 3, so it's going to be 0.75 to the third power, times q. Q is 1 minus p. So if p is 0.75, q is going to be 0.25. because 1 minus 0.75 is 0.25. So Q is 0.25, and we raise that to the n minus x power. So that's going to be 2. Alright, and so I'm not sure if you're familiar with factorial. Hopefully you are, since you've already taken the probability, one of the probability tests. But you know, you can simplify this pretty quick. That's 5 factorial over 2 factorial times 3 factorial. Okay, and then we could simplify the numerator by making it 5 times 4 times 3 factorial. Stop there, and the 3 factorials cancel out. And so what you have is 20 divided by 2 factorials, 2 times 1. So 20, 4 times 5, or 5 times 4 is 20, divided by 2 is 10. And you'll want to say 10 times 0.75 times 0.75 times 0.75 times 0.25 times 0.25. When you do all of that, you should get 0.263671875. And the problem asked me to round to 3 decimal places. So if I round to 3 decimal places, I'm rounding this place, you want to round that up to 0.264. Okay. All right, a brand name has 40% recognition rate. Assume that the owner of the brand wants to verify that rate by beginning with a small sample of 4 randomly selected customers. What is the probability of exactly 3 of the selected customers recognize the brand name? Alright, I would use, okay, here's your P. Your P is 40% or 0.4. So that's the first thing you need to write down or understand. That's success. You know, a brand has a 40% recognition rate. So our P is 0.4. And since it is 0.4, you remember that table? This table right here, it does have 0.4 as a probability, as a P, sorry, as the success or the recognition in this problem. All right, so we need to see what our n is equal to. That would be the sample of 4, and we want to know the probability that exactly 3. So the 4, that's your n. Exactly 3, that's your x. So if we go back to our table, all right, so we said that our n was 4, our x, we wanted exactly 3. So go over to the random variable and go to 3, exactly 3, and the p was 0.4. So if you go over to 0.4, you can see it's 0.154. That's the probability of exactly 3, 0.154. You see the answer right there? What is the probability that all of the selected customers recognize the brand? Okay, so that would be all 4, right? So if we go back to our table, we want to use the same n. It's just that the x, all 4, would be this 4 here. And we go over to 0.4, right there, 0.026. So this is that all 4 recognize the brand. 0.026. Alright, what is the probability that at least 3? What does at least 3 mean? At least 3 means 3 or 4, right? If there are only 4, and we want to know the probability that at least 3 of them recognize the brand, then I'm going to have to say the probability of 3 plus the probability of 4. So take the answer from part A, that was the probability of exactly 3, and take the answer from part B, that was the probability of exactly 4, and add those together, and that'll give you what we have here in C. Alright, if 4 customers are randomly selected, is 3 an unusually high number of consumers that recognize the brand name? Alright, so what is the probability that of at least 3? What did we get? Probability of at least 3? I'm sorry, not at least 3, but exactly 3. We got 0.154. So is that an unusual probability? No, because that's 15.4%. So remember, unusual would be less than 5%, or less than 0.05. So we have here no, because the probability of 3, that 3 or more of the selected customers recognize the brand, is greater than 0.05. Assume that a procedure yields a binomial distribution with n trials and the probability of successes for one trial is p. Use the given values of n and p to find the mean mu and standard deviation sigma. Also use the range rule of thumb to find the minimum usual value and maximum usual value. Alright, so the formula for mean of a binomial distribution, that should be on your formula sheet. Here's formula sheet. The mean of a binomial distribution, mu, is equal to n times p. So for this problem, I need to say n times p. Put this up here. And it gives me, this is problem number 14, gives me that n equals, and I'll write down that formula for you, mu equals n times p. The problem gives us that n is 70 and p is 0.25. So 70 times 0.25 will give you 17.5. Alright. This symbol right here, that's sigma, that's standard deviation. So we must have a formula for standard deviation of a binomial distribution. We'll go back here to our formula sheet. Let's see, look at this one. Here's the variance. Here's the standard deviation. So the standard deviation is the square root of n times p times q. I like these formulas a lot better than the other sets of data we've looked at, right? These formulas are definitely a lot easier to deal with. Alright, so, well, we were given n and p, but we weren't given q. Well, that's okay, because we can figure q out. Remember that p is success and q is failure. So p plus q must always equal 1. I don't know if you've come to that realization or not, but the success of something happening and not happening adds up to be 1. Alright, so if I want to figure out what q is and I'm given n and p, then what would I do? To find q, if I solve this, q is always 1 minus p. Alright, so if p is 0.25, that's what I was given in the problem, then q is equal to 1 minus 0.25, which is 0.75. Alright, now let's just plug that in the formula. Sigma, standard deviation, is equal to the square root of, our n was 70, our p was 0.25, and our q was 0.75. Alright, if you are using the Windows calculator, to me the easiest way to do something like this is to multiply the stuff underneath first. So 70 times 0.25 times 0.75, get that answer, and then take the square root of that. So square root. So you see we got 3.622 2844, so on and so forth. So I'm going to write that down. All right, that's equal to 3.622844. That should be good. All right, and let's see what the next problem or the next step is. Yeah, and see, notice that they did round out to one place. So they round that to 3.6 right here to one place. Now the range rule of thumb says that if we take the mean and subtract 2 times the standard deviation, then we'll get the maximum and minimum usual values. And so anything between those two values would be usual. Anything that's less than the minimum or greater than the maximum would be unusual. So when I do this, I try not to plug in rounded values. I try to harp on that. But when you're plugging things in formula, even plugging in 3.622844, that's a rounded value. So when you plug things into other formulas, if you can keep the numbers exact or as close to exact as possible, you need to do so. Alright, so our mean was 17.5. We want to find mu plus 2 times the standard deviation. So we had 17.5 plus 2 times, and then our standard deviation. You know, if you still haven't your calculator, you might want to use that. You know, if you know how to use the memory button in your calculator, you might want to use that. But I'm going to just keep this in my calculator and say that times 2 equals, and now plus 17.5. Alright, and so my maximum usual value, how did I know it was maximum? Because I added. If you're adding, it's going to be the maximum. That's 24.745688, and so on and so forth. When you put it in, it does ask you, that's actually the second one you find, it does ask you to round to 1 decimal place. So, you know, if I would have just rounded and put in a rounded answer, I may not have got 24.7. I may have, I may not have. Who knows? I guess you could look if you wanted to, but if I round to one place, I'm rounding this place right here, so that's going to be 24.7. Alright, now let's find the minimum usual value. If you find that, that's mu minus 2 times standard deviation. So the mean was 17.5. That's minus 2 times the standard deviation. I'm going to try to keep it exact as possible, but I don't have it stored in my calculator anymore, so I'll just carry it out to that many places. That should be good. Alright, so I'm going to say 17.5 minus, now just to be safe in this calculator, I'm going to put this in parentheses. Parentheses 2 times 3.622844, close parentheses. Alright, and so I got about 10.254312. Now if I round that to 1 decimal place, that'd be about 10.3. You see that's what they have here, 10.3. Alright. Several psychology students are unprepared for a surprise true-false test with 12 questions, and all of their answers are guesses. Alright, we've all been there at one time or another. We've had to guess on something. If you guess on a true-false test, what's the probability of getting one right if you're just talking about one question? Well, if you guess true or false, there's just 2 outcomes. So the probability is 0.5, right, or 1/2 to get the problem right. Find the mean and standard deviation for the number of correct answers for such students. So to find the mean, we say n times p. You say, but they didn't give us an n, they didn't give us a p. Well, we have to read the problem and just, you know, figure out what we need and then figure out what those are. So we were told there were 12 questions. That's our n. What's the probability of getting one right? Or what's the percentage? You know, you're going to get one right, 1/2 or 0.5. So I'm just going to put 0.5. You put 1/2 if you want. Same answer. And that should give us the mean. So 12 times 0.5 or 6. Alright, standard deviation. Remember, standard deviation is the square root of n times p times q. So that's 12 times 0.5 times 0.5. Alright, so that's going to be the square root of 6 times 0.5 is going to give me 3. Square root of 3. I think square root of 3 is about 1.73 something, something, something. That's just from working with it so much. But let's see. 1.73205, whatever. Okay. We want to round to one decimal place. So that would be 1.7. Okay. Would it be unusual for a student to pass by guessing and getting at least 4 correct answers? If we want to know if it would be unusual, we need to find the minimum and maximum usual values. Since this is a small number, we probably could just get away by finding the minimum value and seeing if this is smaller than the minimum value. Alright, so we just want to find the minimum usual value. You say mu minus 2 times sigma. So that's going to be 6 minus 2 times, that is our standard deviation is 1.7 or 1.73. I'm going to leave it exact, so I'm going to leave it like that, square root of 3. Alright, and this will give us our minimum usual value. So, let's see. 6 minus 2 times 3 square root equals. Alright, and I got 2.53589. I'm going to round that to one place, just 2.5. So it's about 2.5. So that would be our minimum usual value. So what we want to know is 4, is that less than 2.5? If it's less than 2.5, then it's unusual. If it's greater than 2.5, but less than the max, which I didn't do because I noticed that 4 was a small number, then it is usual. And so I might as well just do the max, even though you could probably get away with not doing it. And to do that, it's going to be 6 plus 2 times the square root of 3. I can just do that really quick. So 6 plus parentheses 2 times 3 square root close parentheses equals 9.5. So about 9.5. So is 4 between those two? Yes. So that means it's usual. So the problem asks, would it be unusual? So no, it would not be unusual. Okay, because 4 was in the range of usual values. All right. This problem is exactly the same as the previous problems we've worked, except, let's see, our P is 5.4%, so be careful whenever you write down your P. So, this is number 16. Your P here I said was 5.4%, but as a decimal, that's 0.054%, or I'm sorry, 0.054. So when we find mu, that's our mean, we want to say n times p. Find the mean and standard deviation for the number of times this letter will be found for the number of times this letter will be found on a typical page of 1900 characters. Alright, so n equals 1900. So mu is going to be 1900 times 0.054. Alright, and that's going to give you around 102.6. Probably exactly 102.6, I guess. Now the standard deviation, it's the square root of n times p times q. So the square root of 1900 times p was 0.054 times q. Remember how to find q. Q is 1 minus p, so 1 minus 0.054. So that means that's going to be 0.946. Alright, and so multiply that out, take the square root, and you should get something close to 9.9. Alright, in an intercepted message, a page of 1900 characters is found to have the letter occurring 137 times. Is this unusual? So what you need to do is find the minimum and maximum usual values. So mu plus 2 times the standard deviation and mu minus 2 times the standard deviation. That'll be the maximum and minimum usual values. And then see, does 137, is that between the two, the max and the min usual values? If it is, then it's usual. If it isn't, then it's unusual. So it looks right here, it looks like you're going to get yes. It is greater. 137 must be greater than the maximum usual value. Alright. Now, if a gambler places a bet on the number 7 in roulette, he or she has a 1 out of 38 probability of winning. Find the mean and standard deviation for the number of wins of gamblers who bet on the number 7 210 times. So the number 7, that really doesn't have anything to do with it. This 210 times is going to be very important because 210 is going to be our n. That's 210. Probability. What's the probability of winning? It says 1 out of 38. So that's our mean. Multiply those together and you should get close to 5.5. Alright, standard deviation is the square root of n times p times q. So we have our n is 200, we have our p is 1 over 38, our q, remember, q is going to be 1 minus p. So 1 minus 1 over 38 is 37 over 38. So plug those in, work it out, take the square root, and you should get about, I think when I did this earlier, I got 2.31967. And if we ran that to one place, 2.3. Would 0 wins in 210 bets be unusually low number of wins? Just if you didn't know anything about statistics and you had bet on something 210 times, I'm not saying like a lottery ticket. I'm saying like, like roulette or something, to that effect. You bet on 210 times and you didn't win any of those times, then of course that's unusual. However, using statistics, we can show that, because if we get the minimum usual value here, how do you do that? Remember, it's mu minus 2 times the standard deviation. That's the minimum usual value. That's, 0 is going to be less than that, because 0 is, that's, no wins. So you'll never get a negative number when you find a minimum value on a problem like this. But if you just want to do it, feel free to. But yes, that is unusual because 0 is below the minimum usual value. Right. What requirements are necessary for a normal probability distribution to be a standard normal probability distribution? Alright, so for a normal probability distribution to be a standard normal probability distribution, the mean needs to be 0 and the standard deviation needs to be 1. Alright, it's not the other way around. The mean is 0, the standard deviation is 1. Alright, the waiting times between a subway departure schedule and the arrival of a passenger are uniformly distributed between 0 and 6 minutes. Find the probability that a randomly selected passenger has a waiting time less than 0.75 minutes. Alright, so you need to take the total time. Alright, remember probability, just a real classic run-of-the-mill look at probability is like part over total. And so we want to take our part, how much time we've been waiting, and we want to divide that by the total amount of time. So if we apply that, it's just 0.75 divided by 6. Because, you know, every minute has the same probability, so find the probability that a randomly selected passenger has a waiting time of less than 0.75. We said 0.75 divided by 6. That should give the answer, 0.125. This is another problem where it says the lengths of the classes are uniformly distributed between 46 and 56 minutes. So again, we want to do part over total. The total time of the class is 46 to 56 minutes. So that's a 10-minute interval. So the total interval here is 10 minutes. Find the probability that a given class period runs between 50.5 and 51.5 minutes. Alright, so how many minutes are between 50.5 and 51.5? Just 1 minute. So 1 divided by 10, or 1/10. Round to 3 decimal places. So 0.100. Alright, now the rest of this chapter, not all of it, but a lot of it, does depend on whether you understand the bell curve. This is where we first start looking at the bell curve as far as getting values under the curve. You say, why would we ever want a value under some kind of crazy bell curve? Well, if the bell curve is a standard or represents a standard normal distribution, then the area under the entire bell curve, whole thing, is 1. Okay? Well, we know something else that maxes out at 1, right? Probability maxes out at 1. The probability of a success, if you know something's going to be a success, is 1. If you know it's going to be a failure, is 0. So we can relate bell curves and area under the bell curve to probability. And the way that we do that is by using z-scores and understanding those z-scores and what word problems are asking. Okay, and so I'm going to help you with that these next couple problems. Now, the first thing that I've noticed about these problems when I was looking at them earlier was that they're shaded from left to right. Well, this one is, and you can look at it. And knowing what I know about statistics and probability, and the way that your book teaches this, if you've had another statistics class, this may be a little different. but we always want to look at if we're looking at area under the bell curve, we always want to think about the area cumulative from left to right. And the reason for that is that's the way that the textbook sets up their z-scores. If we look at the z-score chart, which should be on your formula sheet or at the back of the book, you'll notice on the z-score chart it says cumulative area from the left. So I know you may not remember what a z-score is, or I'm going to refresh you on that. But anything we look up in here, all these little numbers in here, these are all areas. And they're all areas under the bell curve, cumulative from left to right. So if we get halfway, right here, this is where the mean equals 0. If we get right there, the area, we're halfway under the bell curve, so the area to the left is going to be 0.5, right? Well, look at all of these negative z-scores. As the z-scores get larger and larger, getting closer and closer to 0, what does the area do? It gets closer and closer to 0.5, or 1/2, and that's not a coincidence. When we go to the right of 0, well, what would the right of 0 be? If this is 0, if we go to the right of 0, that's where z-scores start getting positive. Then the area from left to right is going to be greater than 0.5. It's going to get larger and larger and larger. Well, look at these. Positive z-scores. These positive z-scores are getting larger and larger and larger as we go to the right, further and further and further. All right, so what this bell curve shows us is area under a curve cumulative from left to right. And to use that, most of the time we can figure out a z-score, and with the z-score that will correspond to an area. Then in turn that area represents a probability. Alright, so these first few problems, you're not given, like a certain situation, you're just given the raw numbers. And they want you to use the table to find the area. Find the area of the shaded region. Alright, so since this table is cumulative from left to right, that means if I want to know the area to the left of a z-score, so that's why this is all shaded to the left, then I just take the value out of the table. If for some reason I wanted to know this over here that was shaded, I would have to use a z-score of 0.78, find that in the table, find the area that corresponds to that, and then say 1 minus. Okay, so if you want area to the left or less than or up to that z, you take the value in the table. If for some reason you wanted the area to the right of a z-score, you say 1 minus the area given in the table. Alright, so let me show you what I'm talking about. And if that confuses you, don't worry, we're going to work several of these. Alright, so number 21, our z is 0.78. That's 0.78. Z-scores are always rounded to 2 places. Okay? Now, just because this is 0.78, that doesn't mean that's why this answer is 0.78. We have to use the table. So 0.78 is positive, so go to a z of 0.7. See, there's 0.7. And then the hundredths digit is up at the top here. So go over till you get to 8.08. Alright, so 0.708. See, 08 is up here. Alright, and so that's going to be 0.7823. What does that mean? That means the area cumulative from left all the way up to that z of 0.78 is 0.7823. So So that's your answer, 0.7823. Alright, notice this. Okay, this is the area to the right of a z. Now, the way the table's set up, if I look up z equals negative 1.15, it's just going to give me the stuff up to a z of negative 1.15. So it's going to give me the area of this white region here that's not shaded. Now, since we know that the area under the entire bell curve, or the entire curve here, is 1, I told you that earlier, the area under the bell curve is equal to 1, which corresponds to a probability. What we can do is we can get the area that's given for z equals negative 1.15, and we can subtract that from 1, and that'll give us the shaded region. Okay, so let's do that. Let's look up the area for negative 1.15. These are positive z-scores. The negative z-scores were first. Alright, so negative 1. We want to go to negative 1.1. So negative 1.1. Now I need to know which column is 5. Alright, it's going to be this column right here. So that's going to be the one to the right of this little star. I have to remember that. Alright, negative 1.15. So 0.1251. 0.1251. Now 0.1251 is not my answer. 0.1251 is this area right here of this unshaded region. So if I want to get my answer, I have to say 1 minus 0.1215. That's going to give me 0.8749. Not exactly. I'm just looking at the answer right here. Let's see what that would give me exactly. Let me double check everything. That's negative 1.15, negative 1.15. We said was at that star, so 0.1251. So 1 minus 0.1215, 0.8785. 0.8785 is not the answer. I must have got off on my columns. Negative 1.15. Here's the 5. Negative 1.15. That is the right answer. If that is the right area. Negative 1.15. Oh, I blew it up, so that's really big. I'm going to zoom that back out just a little. Alright. That should be the answer. So I should be able to say you subtract that from 1, so what I'm going to do is make it negative 1 and add 1. Alright, so that is the answer. And it's probably some small rounding area. A lot of times the computer may use a different formula so they get it more precise or more exact. So if you're using a calculator or you're using calculus to figure this out, that's probably how they got even more exact than was given. Hopefully we don't run into that problem anymore. If I see a lot of people miss that problem, then I'll make sure that I give everybody credit for it. But a lot of times this program will take answers if it's a couple hundredths off or a couple thousandths off because of rounding and stuff like that. Alright. So now we want to find the area between these two z-scores. So what you want to do is you want to find the area to the right for the right z-score, because what's that going to do? If I find the area for the right z-score, that's going to give me all of this here, everything up to that point. Alright, and so you'll take that answer, and then you'll look at the area for negative 0.83. That'll be all this. And so if I take all the way up to that point, all the way up to the z equals 1.22 answer, and I subtract out this, then I'll have what's between the two. Okay, so that's what I'm going to do. Find the area for 1.22. So let's go to our table. Zoom out here. I think it just opened up in the window. Yeah, there we go. So again, we were looking for z equals 1.22. That's negative z-scores, positive z-scores. 1.22. That's 0.8888. So 0.8888. That's the area up to that point. Now we want to subtract the area we get out of the table for negative 0.83. So table negative. So we go back to the negative. Negative 0.8. And I believe 3 is right here. But let me double check. 3 is actually the fourth column. Okay. Alright. So negative 0.83, negative 0.83, 0.2033. So minus 0.2033. Let's do that in my calculator. We'll get a little more exact this time. Minus 0.2033. So that's the area between the two curves, 0.6855. Alright, and that's right on, 0.6855. You see down here, it pops up correct answer. It has the plus or minus there. That means that it'll accept different answers just really close to that. Alright. Now, this is a little different. You see there's nothing shaded here. It says, find the indicated z-score. So the z isn't given. The area is given. Alright. So what we want to do is we want to go to our table and we want to get as close to this area as possible. Now remember, the area that's the stuff on the inside. These numbers here. So our problem wanted us to get as close to 0.8980 as possible. So you can see the biggest area in the negative z-score chart is 0.5. So if we're looking for 0.8, we have to go to the positive z-scores. Right? We're looking for 0.8980. So 0.8, 8, 0.88, 0.89, keep going, 0.8980. It's this one exactly. Alright, we just have to figure out which row and column we're in. Alright, our row is 1.2. And then we want to go straight up in this column. Let's see what column. Alright, here's our number, 1.27. 1.27 is our answer. That's the z-score that would correspond to this area. This is another, we're given the area, find the z-score. This area to the right of the to the left of the z-score is 0.2877. So we want to find that area in the table. Go back to our table, and we're looking for 0.2877. Well, 0.5 is as small as we get on the positive z-score, so we need to go back to the negatives. 0.26, 0.29, let's see, 0.27. Getting closer. 0.27, 0.28, 0.2877, right here exactly. So that's, I zoomed in again. 0.2877. That's going to be a negative 0.5, and then see which column this is. It was the 6th column. So negative 0.56. Right. Negative 0.56 is 0.2877. So that's your answer. Negative 0.56. Alright, this is a little tricky because this gives us the area to the right, but the way that the table reads, it only gives us areas to the left of the z-score. So what we have to do, if we want to find the z-score, that would give us an area that corresponds to greater than z. We have to say 1 minus to get the area on this side, and then look that up in the table. That will give us the right z-score. So we want to say 1 minus 0.1762. That's the area that we want to look up in the table, 0.8238. We look up 0.8238, we'll have our answer. So it's going to have to be a positive z-score because it's bigger than 0.5. 0.8238 right here. That's going to be 0.93. 0.93. 0.93. Alright. Assume that a randomly selected subject is given a bone density test. Those test scores are normally distributed with a mean of 0 and a standard deviation of 1. Find the probability that a given score is less than negative 1.24. Alright, here's where we're starting to get into keywords. Less than. Less than is area to the left of the z-score. Greater than or more than will be area to the right of a z-score. Alright, so this problem wants to know, find the probability that a given score is less than negative 1.24. Now, for all of these graphs, the mean is 0 and the standard deviation is 1. Okay, that's why they look like they do. They don't look like a regular bell curve there. And so we want to know which one of these graphs has the area to the left of negative 1.24 sketched and shaded. Remember, negative z-scores are on the left side of the center, so it's got to be this one right here. Got to be this one. It's not this one because that's shaded to the right. It's not this one because it's in between two z-scores. It's not this one because that's a positive 1.24. The problem says negative 1.24. Alright, and then to find the probability, you simply go to your table, and now we're not looking at areas now, we're looking at negative, what was it, negative 1.24. Need to look that up in our z-score chart. Negative 1.24. It's right here. 0.1075. And that's the answer to the second part of that question. All right, 0.1275. All right. This is looking at more of these graphs or more of these bell curves with a mean of 0 and a standard deviation of 1. This is standard deviation of 1 degree Celsius. It's talking about thermometers. And we want to know the probability of, if we grab one thermometer from this set of thermometers, that at 0, the reading is between negative 1.11 and 1.63. So between two numbers, this is a negative z-score, this is a positive z-score. So if we look at these three graphs, it looks like this one would be, the word problem would say less than negative 1.11. Well, that's not what our problem said. Our problem said between. This one right here, if it would have said greater than 1.63, then we would use this one. Well, ours said between, so this is the only possible choice. Okay. And to find the probability, look up the area for 1.63 in your z-score chart, and then subtract the area for negative 1.11 in your z-score chart. And you're going to come up with 0.8149, or something close to that. Really, really, really close. Again, the area from the furthest one to the right in the z-score chart minus the area for the one to the left in the z-score chart. Now, this is another one of those where we're given, let's see, we want to find the area, okay? Here's how this is different. Find the area of the shaded region. The graph to the right depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. So it doesn't tell us what the area is. It doesn't give us a z-score. Oh no. Well, it does give us a value. This is like an x value. This would be an IQ of 95. So we have to figure out a z-score of 95. How in the world would we do that? Well, we have to use the formula for a z-score. The formula to find a z-score is z equals x minus mu over sigma. Most of the time in your word problem, if you want to find a z-score, the mean and the standard deviation will be given. Okay? And then if we're looking at an actual value, like we're wanting to know less than something or greater than something, that's going to be your x. Okay, so in this problem, the problem doesn't actually tell you this, but what we have shaded right here, that is the area under the curve, or the area under the bell curve, less than 95. So what this represents is the probability that a randomly selected person would have a z-score less than 95. Alright, so the 95, that's our x. So if we want to find our z-score, we have 95 minus, we were given in the problem that the mean was 100 and that the standard deviation was 15. Alright, and so that'll be negative 5 divided by 15, or what is that? Negative 1/3. So we want to, for a z-score, we want 2 decimal places. You punch that in your calculator, and you're going to get negative 0.3333, repeating. That 3 is going to keep going on and on. So if we want to round the 2 places, because it is a z-score, then we round that to negative 0.33. Alright, so that's our z-score. You say, that's not the answer given. Well, that's not, it doesn't say what is the z-score. It wants us to find the area of the shaded region. So now that we have a z-score of negative 0.33, we can go to our z-score chart and look at negative 0.33, and it'll give me the area that was shown there. Alright, now this right here, this is negative 0.3, and then this is the 0 column, the 1, the 2, the 3. So this is the area for a z-score of negative 0.33, 0.3707. Go back to our problem. That will be the answer, 0.3707. Yep, 0.3707. Notice that it has plus or minus, and that allows for a bigger error because we rounded there. So if you were using a program, not the actual table, using a program to find it, it's going to give you something different than that because we rounded our z-score. That's why. And you have to round the z-score to use the table. Alright, well, we're on problem number 30. Find the area of the shaded region. Okay, so again, we're talking about IQ scores. We have a mean of 100 and a standard deviation of 15. So we need to find a z-score for the far right value and then find a z-score for the far left value. Because if we want to know the area between the two, then we want to know what area we would get for a z-score where x was 125, and then take that and subtract the area from the table that you would get for a z-score of 85, well, where x is 85. So we need two z-scores. I'm going to call one z sub 85, that's the one furthest to the left, and I'll call the other one, when I work it out, I'll call it z sub 125. That's just so I can keep it straight in my head. And remember, the 125 was furthest to the right, so I want to take that area and then subtract the other area from it. Well, how do I find these z-scores? I use that same formula, x minus mu over sigma. So x is 85, mu is 15, mu is 100, and the standard deviation, the sigma, is 15. Alright, so I believe that's going to be negative 15 over 15. So I don't need a calculator for that one. That's just 1, or negative 1. Remember, you got to do 2 decimal places though, so it's negative 1.00. Right. Find my other z-score. That's going to be 125 minus 100 over 15. That's 25 over 15. 5 over 3. You can do any of this in your calculator. If I was to say 5 divided by 3, 1.6 repeating. So if that's 1.6 repeating, that's going to be 1.67 as a z-score for my chart. Alright, so we want to find the area of the one furthest to the right. So let's find the area that the z-score chart would give us for 1.67. It's a positive z-score. Alright, 1.6, and then go over to the 7s column. So that's 0.9525. So our area up to that point is 0.9525. Alright, let me show you again what that would be. That would be all this right here that's not shaded, and all this that's shaded up to that point is 0.9525. Now I want to look for this area right here in the z-score chart and subtract that, and that'll give me the area between the two. Alright, so that's minus I'll find the area for 85. We found a z-score of negative 1.00. Let's go back to our tables. Negative, look at the negative chart. Negative 1.0, and this is a 0 column. So that's 0.1587. So minus 0.1587. Subtract that in your calculator, and you should get 0.7938. That's the area between the two. Let me tell you what that actually means. You know, this stuff makes a lot more sense if you understand, you know, what this is showing here. Alright, so if these are IQ scores, we know that the mean IQ score, and this is just in general, is 100. Okay? So 100 is around here somewhere. We're finding the probability that if we randomly select one person, that their IQ score is between 85 and 125. So what is the probability that if we randomly select one person, their IQ score is between 85 and 125? We found it to be 0.7938. So that's 79.38% of the time. So almost 80% of the time. If you randomly select one person, their IQ score would be between 85 and 125. Alright. Now we have to really pay attention to the wording on this problem. Assume that adults have IQ scores that are normally distributed with a mean of 105. So that's a little different, you know, depending on what source you're looking at or what, you know, what set of data people have used. They may have a different mean or standard deviation. This mean is just a little different. Okay, mean of 105 and a standard deviation of 15. Find P sub 9. Oh, remember our friend Mr. Percentile. So we want to find the 9th percentile. That's the IQ score separating the bottom 9% from the top 91%. All right, so let's draw a picture of that. So if we have our bell curve here, we want to know the 9th percentile. So how do you write 9% as a decimal? 9% is 0.09, right? So that is an area. So like not even, that's not even 0.1. It's not even a tenth of this. But let's just pretend that area is 0.09. Okay, we're trying to figure out the IQ score. That's the IQ score, the actual X value here. So like on the previous problems where we were given the number, we're trying to figure out that number. We're not trying to figure out the z-score, we're trying to figure out that number. Now to figure out that number, I'm going to have to use my z-score formula. Okay, so how would I use that z-score formula? Because the z-score formula is z equals. It's z equals x minus mu over sigma. Alright, so like any formula though, you can always solve for any of the variables. So how could I solve for x? If I multiplied both sides by sigma, those sigmas cancel out, and I would have sigma times z, or z times sigma, equals x minus mu. Now if I want to solve for x, you add mu to both sides. So x equals mu plus, I usually write z times sigma, not sigma times z. But you can write it either way. So the x value is equal to the mean plus the z-score times the standard deviation. Alright, so let's see what we're given in our problem. We were given a mean of 105. We were given a standard deviation of 15. And we don't have a z-score. It's not given to us. It doesn't say z equals. In a way, it is given to us, though. If we're looking for the 9th percentile, that means that that section is an area of 0.09. So if I look that area, not the z-score, if I look that area up in the z-score chart, that will correspond to a z-score that I can use in my formula. I have the mean, I have the standard deviation. I was given I want the x value, so I had to solve my formula for x. I just need to figure out the z-score that corresponds to an area of 0.09. So I go to my z-score chart, and I'm looking at these areas, not at the z-scores at first, these areas. I want to get as close to 0.09 as I possibly can. Alright, so let's see, 0.02, 0.09, 0.093. What are we looking for? Try and get as close to 0.09 as possible. It looks like this right here. It's not exactly 0.09, but it's 0.0901. That is as close to 0.09 as I can get. So let's see, what z-score does this correspond to? Negative 1.3, that's 1, 2, 3, 4. Negative 1.34 corresponds to an area of 0.0901. And that's as close to 0.09 as we can get. So write that down, negative 1.34. Alright, so our z, right here, that's negative 1.34. What was our standard deviation given in the problem? 15. What was our mean given in the problem? 105. Work that math problem out. Probably be easiest to multiply this first. So 1.34, make it negative, times 15, and now add 105 to that. And I got 84.9. Remember, we're using all kinds of rounded values, whether we know or not. So let's see if that's the exact answer. Yeah, that's the exact answer. 84.9. You see it does have a little error correction down there, so that's what all that little stuff is showing. Round to the nearest hundredth, so you want to add a 0 to that. Alright, the lengths of pregnancies are normally distributed with a mean of 267 days and a standard deviation of 15 days. We're talking about pregnancies now. Find the probability of a pregnancy lasting 109 days or longer. Key word here, 109 days or longer. That's very important to our problem, the or longer is. Okay? So let's write down what we're given, and let's figure out what it wants us to know. We're working on part A. Alright, we're given a mean of 267 days. Right, mean equals 267 days. We're given a standard deviation of 15 days. And we want to know the probability of a pregnancy lasting 309 days or longer. So our x is equal to 309, but we need to remember or longer. That's like or greater or more. And so we can figure out a z-score for this. Z equals x minus mu over sigma. It's going to be 309 minus 267 over 15. And when you work that out, you're going to get a z-score of 2.80. Okay? So, what are we actually finding? Well, somewhere under this curve, probably over here somewhere, there's a z 2.80. If we look that up in our chart, that's going to give us the area up to that point. Remember, the chart gives you the area cumulative from left to right. Our problem wants to know, though, find the probability of a pregnancy lasting 309 days or longer. So more, greater than. Greater than, we want to know the area to the right. So the way that we find that is we say 1 minus the area that we're given in our chart. How do I know, again, to say 1 minus to get this stuff on the right side? It's because it was or longer or greater than. If the problem says more or greater, then you say 1 minus the area given from the chart. Okay? So 1 minus, now I need to find what area does 2.80 give me. So I go back to my chart. It's here somewhere. All right, so 2.80, 0.9974. Okay? So that is the area up to that point, up to that z-score. So all that stuff I had here, that area, 0.9974. That's not what I want. I want more than or greater than that. So I say 1 minus 0.9974, and that will give me 0.0026. So what does that actually mean? That means the probability that a pregnancy will last more than 309 days is 0.0026. Or that's the same thing as 26 out of 10,000. Or you can think of it like 0.26%. Okay? Part B says, if the length of pregnancy is in the lowest 4%, then the baby is premature. Find the length that separates premature babies from those who are not premature. So we have all these births, we have all the data, how long it took. All of it's under our bell curve. We want to know the value that separates the bottom 4% from the top 96%, because that's going to be the place where pregnancies are considered to be premature, according to this. So if we know that bottom is 4% of the total, then we look up, we have what? We have an area of 0.04. Now what are we looking for? We want to know the length of time that separates premature babies from those who are not premature. So an actual day, the length of time. That's an x value. We want to know the x that's there. To find the x, I'm going to have to use the z-score formula and solve for x. We've already done that before, so we have x equals mu plus c times sigma. What do we have and what do we need to find? We were given the average, or the mean. We were given the standard deviation. To find this x value, we need the mean, the standard deviation, and the z-score. We weren't given the z-score, but we were told that this 4% represents the length of pregnancy that would be premature. So if we look up a z-score that corresponds to 0.04, then we'll have everything we need to find x. Right? Again, we were given that was 267. We were given that the standard deviation was 15. We just need to figure out what z-score corresponds to an area of 0.04. Let's go to our chart. An area of 0.04. So look at our z-score charts. We want to get as close to 0.04 as possible. There's 0.05. There's 0.04. Let's see how close we can get. 0.0401. Okay, so I did it again. Let me get out of that. 0.0401. Going too far. That's going to be negative 1.7. See, negative 1.75. Negative 1.75. So our z is negative 1.75. If we solve our, work that out, that's going to give us the amount of time or the length of pregnancy that would separate when a baby is premature or not premature, according to this study anyway. Okay, so we need a calculator to do that. So it's 267 plus, I'm going to put this in parentheses to be safe, parentheses 1.75, make it negative, times 15, close parentheses, equals 240.75. Alright, so we would want to round to the nearest integer, it says, so that would be 241. So according to this problem, this study, babies who are born on or before 241 days are considered premature. Alright. Now, I've had a lot of questions in the homework about these problems. And it may be because you didn't know exactly what to do, how they were getting the numbers, the probabilities. Alright. There are 3 or 4 of these problems in a row, and I would have to say out of all of those, this one probably takes the longest. Okay, so I'll make sure that I go through this one, and I may speed through the other ones, but I'm going to take my time on this one. Alright, 3 randomly selected households are surveyed. The numbers of people in the household are 3, 5, and 10. Assume that samples of size n equals 2 are randomly selected with replacement from the population 3, 5, and 10. Listed below are the 9 different samples. Alright, so these are the different samples. You're taking 2 of these with replacement. So if you had these 3 numbers in a hat and you drew out one, and then you put that number back and you drew out another, these are your sample sizes, or your different samples you could have. Okay, find the variance of each of the 9 samples. So what is variance? Variance, remember, is a standard deviation squared. We had a formula a few chapters back for standard deviation. Alright, and it was n times the sum of x squared minus the sum of x squared all over n times n minus 1. And this is how you find the standard deviation. Well, the variance is the standard deviation squared. So how do I find the variance? I take the radical off. Okay? The variance is this formula. And this is for a sample, the variance of a sample. Alright? So, we want to find the variance for each set of numbers. Yes, that's a lot of sets of numbers. Okay? But think about each set like it's its own data set. So what I did is I listed the x values, 3, 5, and 10. Then I made a column of x squared. That'll be 9, 25, and 100. Now here's what I need. I need this, though, from each set. Not from these three numbers together, but, for example, for 3, 3, for the set 3, 3. Think about this like this is the sample. That's two numbers, 3 and 3. Now for this set, the sum of my x values would be 3 plus 3. That's 6. The sum of my x squared, well, 3 squared was 9. So that's 9 plus 9, or 18. Alright, so what's n equal to? I have two numbers. N equals 2. So if I plug this in this formula up here, I will have the variance for this set. I'll go ahead and tell you it's going to be 0 because there's no varying between 3 and 3. Those numbers are the same. It works out like that for any of the sets to have the same number. But let me work it out. There's two numbers, so 2 times the sum of x squared is 18 minus the sum of x is 6 squared, don't forget that, over 2 times 2 minus 1. So this is 36 minus 36 over 2, or 0 over 2. So what is the variance for the set of numbers 3, 3? It's 0. You have to do that for every set of numbers, okay? Once you do that for every set of numbers, you're going to get 3 of them that's going to give you 0. You're going to get 2 of them that's going to give you the answer 2. You're going to get 2 of them that's going to be 12.5. And you're going to get 2 of them that's going to be 24.5. So work out the variance for each set of numbers. Then to find the probability, you count up how many zeros do you have. There's 9 sets. If you find 3 zeros, the probability is 3 over 9, or 1/3. If you find 2, okay, and then you look and you say, well, how many 2's do I have? How many of the set's variance is equal to 2? You'll have 2 of those. That's why the probability is 2 out of 9. Then you're going to have a couple, 12.5 is a variance, 2 to be exact, on this problem. You know, your numbers are going to be different, so, but that's how you find those. That's how you find the variance, and then that's how you find the probabilities. Count how many of each, and then write the probability of whatever number you're writing down or you click. It does say use ascending order, so make sure you start with the smallest and go to the largest for variances. Now, I got hung up on this next part because I haven't done a lot of variance in a while. The next part says compare the population variance to the mean of the sample variances. Alright, there's two things here. Population variance. We haven't done a lot of population variance or population standard deviation. Usually you're given that. So that formula is a little different. I'm not sure if you remember that formula. Let's see if I can pull that formula up. I know it's in your textbook. You look at the formula for population standard deviation and then take the square root off. Let's see if we view an example, if it gives us the formula. Alright, here it is right here. It's in your textbook, I promise you. Something to that degree is. And so that's how we find the population variance. So you're going to need to find x minus mu. You say, what's the population? Well, for this problem, the population of numbers is 3, 5, and 10. So if we follow our formula, I know I didn't have it up there long, I can write it down. Our formula was x minus mu squared all over n. So what we want to do is we want to find x minus mu for each data item, then square it, and find the sum of all those. So if I have, what's one of the first data items? What's the first data item in my population? Let's say 3. We know that, well, we need to make sure we find the mean of the data items too. So to find the mean, you add them all up and divide by 3. So you get 6. Alright, so say 3 minus 6 squared. That's going to be negative 3 squared, or 9. Then say 5 minus 6 squared. That's going to be negative 1 squared, or 1. And say 10 minus 6 squared. That's going to be 4 squared, which is 16. Now for our formula, this is for variance, population variance. You want to add those together because we want the summation of that. So that's going to be what, 26. And then divide by n, the number in our population, or in our whole population here. 26, our whole population, n is 3. So 26 divided by 3 is 8.6 repeating. So that's the variance. If you want to round it to 2 places, round it to whatever you want to, but that's your variance for the population. Now our problem wants us to compare that to the mean of the sample variances. What is mean? So you add up all the sample variances, not these 4. You have 9 of them on your paper if you've worked all these variances out. Add all the variances up, so it'll be 0 plus 0 plus 0 plus 2 plus 2 plus 12.5 plus 12.5 plus 24.5 plus 24.5. Divide that by 9, and guess what? You're going to get 8.6 repeating. So you're going to get the same thing when you find the mean of the sample variances. You're going to get the same thing as you did when you found the population variance. Since it's the same, that means that the population variance is equal to the sample variances. That means that it actually targets. Down here, if you'll look, let me go over these questions. Compare the population variance to the mean. Choose the correct answer below. The population variance is equal to the mean of the sample variances. That's what I told you. So what does that mean, though? It says, do sample variances target the value of population variances? In general, do sample variances make good estimators of population variances? Why or why not? The sample variances target the population variances. They do because they're equal. Therefore, sample variances make good estimators of population variances. So, not just for this set of data, but for any set of data. Variances make good estimators. They're unbiased estimators, they're called. That one definitely took the longest. You do the same thing on this problem, except we're not looking at variances. Thank you, right? Yeah. Yeah, you're doing median here. So, like I can show you real quick. How do you find the median of 2 numbers? Well, think about this like that's the set of data. The median, since there's an even number of numbers, you add the 2 and divide by 2. You say that's finding the mean. Well, if it's only 2 items, the mean and the median are the same. Alright, so 2 plus 2 is 4 divided by 2. So the median is going to be 2 for that. The median for that's 6 divided by 2. It's going to be 3. 11 divided by 2. That's 5.5. 8 divided by 2 is 4. No, I'm sorry, that was 6 divided by 2 is 3. 8 divided by 2 is 4. 13 divided by 2, that's 6.5. And you do that for the rest. I'll just write these others down. It's going to be 9, that's going to be 5.5, and that's going to be 6.5. Alright, so you have, these are your different medians. Alright, now find the, whenever you do that, then it's real easy to fill in this little chart here. Start out with a sample median of 2. How many of those have a median of 2? Only one of them, so 1/9. Sample median of 3. This one has 3, and this one is 3. So there's 2 of them, so it's 2 out of 9. And you do that for the rest of your medians. That's how you get the probabilities. Alright. Now, we want to compare the population median to the mean of the sample medians. So you need to find the mean of all these medians. So add them all up and divide by 9. Okay? And that's going to give you, I think you get 5 when you do that. So the mean of these medians is equal to 5. Alright. Now what is the population median? Well, what were our numbers again? This is our population up here, 2, 4, 9. So what would the median be? The number in the middle, 4. So for the population, I guess you could say population median, that's 4. Are they the same? No. That means it's a biased estimator. It doesn't target the population or the sample medians. The mean of the sample medians doesn't target the population median. But let's see what the questions ask. Compare and then choose to write below. The population median is not equal to the mean of the sample medians. Do sample medians target the value of the population median? No, they do not. Do they make good estimators? No, they do not. That makes them a biased estimator. So it's a same thing on this one, except we are doing means. Now, it does not give you the sample sizes. It says this, or it doesn't give you the actual samples. It says the sample size is 2 on this one. So what you're going to need to do, and also does it say with replacement or without replacement? With replacement. So what you're going to need to do is you're going to need to figure out all the sample sizes. So if those are our 4 possibilities, and we have replacement, and we have sample sizes of 2, you're going to have 44, 44, 44, 34, 44, 29, 44, 17, and you're going to want to go through, that's just with the 44s, you're going to want to go through, do the same thing, 34, 44, 34, 34, 34, 29, and list all those. It's going to be 16 different ones, so it is going to take you a little while on this problem. But what are we trying to find? Hopefully it's not standard deviation or variance. That would take too long. Once you have all these, let's see. Find the mean of each sample. So that's really easy. Add the 2 numbers and divide by 2. So do that for all 16, and you're going to have a bunch of means. Then count how many 44s you have. Count how many 39s you have. And and then how many you have, you put that over 16, since there were 16 total. Find the mean of the sampling distribution. So what is the sampling distribution? And what does its mean? Looks like you're going to get 31. Is the mean of the sampling distribution from part B equal to the mean of the population of the 4 listed values? So once you found the average of all these means, you get 31.00. Is it the same as the average of these, or the mean of these 4 numbers, these 4 data items? Add them all together and divide by 4. And you're going to get 31 for that as well. And so, is it always equal? Yes, the sample mean is equal to the mean of the population. These means are always equal because the mean is an unbiased estimator. Take a little time, but it's just a lot of plug and chug numbers. On this one, the same thing. This is the sample size. If you figure out the sample size, and then that's actually one of the questions on this one. And then we need to find the range of each set. Remember, range is largest minus smallest. So, like, the range on this first set here is 0. The range here would be 6. Or, I'm sorry, 10. The range here would be 4. The range here is 10, 0, 14, 4, 14, 0. All right, so you have all those different ranges. Then you can come up with the probabilities over here in this column of how many of each you have. Then you can find the range of this set of data, which is 14. And that's going to be different, I believe. Yes, it's going to be different from the mean of all the sample ranges. So that means that it is a biased estimator. So sample ranges do not target the population range. Therefore, sample ranges do not make good estimators of population ranges. All right. 37. This is central limit theorem. All right, let me show you the difference between this and the problems that we've looked at a little earlier today. For part A, let's see what we're given. Assume that a woman's height are normally distributed, or women's height are normally distributed with a mean given by mu equals 62.6 and a standard deviation of 1.8. This is problem 37. Now, part A is not very different from problems we've worked before. It says if one woman is randomly selected, find the probability that her height is less than 63 inches. So for part A, x equals 63 inches, and the key word here is less than. Oh, less than. That means under the bell curve, we want the area less than whatever z-score I would get here. So you take the area that's given in the z-score chart. All right. Less than, you take the area in the chart. Greater than, you say 1 minus the area you get in the chart. All right, so we do have to figure out a z-score. All right, and your z-score for this would be 63 minus 62.6 divided by 1.8. If you do that in your calculator and round, you're going to get 0.22 as your z-score. So then, in turn, you go to your z-score chart. You look up a z-score of 0.22. So 0.22. This right here, that's our answer, 0.5871. So part A, the answer is 0.5871. That is the probability if you randomly select one woman that her height is less than 63 inches, given this information up here. Alright, now here's how these last few problems are different. If 50 women were randomly selected, find the probability that they have a mean height less than 63 inches. That's where the central limit theorem comes in. If we want to know the probability, and it's not just of one person, it's 50. It's more than one. Of course, we have to know that either our sample is 30 or greater. We also have to make sure that either that occurs or the original set of data is normally distributed to apply the central limit theorem. Okay, so since we do have 50 women, then we can use the central limit theorem. So how is it different? Well, that's going to change our z-score formula just a little bit. It's x minus mu over, it's usually just over sigma. Since it's more than just 1, we say sigma divided by the square root of ever how many we choose. Since we chose 50 on this problem, when we find the z-score, we enter in all these numbers up here the same. 63 minus 62.6 over 1.8, but it's 1.8 divided by the square root of 50. So that's how these problems are different. If you choose 50, then we have to use the central limit theorem. That just changes your denominator. So what you might want to do, that's a little tricky in the calculator. What you might want to do is either use parentheses good on your calculator or work out the top, work out the bottom, and divide. Okay? You can work out the top without using a calculator, probably. That's 0.4. Now, to work out the bottom, you could just put it all in parentheses since you have this good Windows or Apple calculator. I'm not exactly sure how good the Apple calculator is, but it has to be comparable. If I use parentheses, let's see if I can do that. Parentheses, 0.4 divided by. Now, got to be careful because this is in the denominator. So I'm going to put parentheses, and then what I'm going to do is start a new parentheses, 1.8, close parentheses, divided by, divided by, right, because that is divided by, the square root of 50. I'll put that in parentheses. Parentheses, 50, square root, close parentheses, equals. So you see, it is very tricky if you want to put it all in at once. So you might want to do the top and then do the bottom. Now, I didn't even find the bottom number. It did give it to me, but I pushed equals too fast. So whatever that equals, that's what goes down there. And this answer that's in the calculator, since I did hit equals, that's going to be what that would equal. So if I round that to 2 places, because it's a z-score, that's 1.57, about. Alright, so let's make sure that we have less than again in the problem, and it is less than. So when we'll look up a z-score of 1.57, take that answer that it gives us. So go to your z-score chart, go to 1.57, let's see, 1.5, that's 1, 2, 3, 4, 5, 6, 7, that's our answer, 0.9418. Alright, so the probability, 0.9418, right there. This problem is exactly the same. We start out and we just want to know for 1. Then on the second problem, B, on part B, we want to know the mean for 15. So when you set up your z-score, make sure where you have that sigma's in the bottom, sigma, but then divided by the square root of n. So when you set up your z-score, make sure that you have, or you plug in the 15 right here, where you have the square root of n. Alright. Now with this problem you need to be careful because it says greater than. So whenever you find a z-score for any of this, and I can give you some, I've worked out all of these. Say, why don't you share with me? Oh, I will. On part A, and I'm just going to go ahead and just jot this down. I know that you're probably sick of hearing me talk, but I do enjoy doing this, so make sure you send me some questions if you have them. But for part A, this is x minus mu over sigma. And you can round that and get a z-score of 1.68. Now, I did notice whenever I worked out this problem, you don't get exactly 0.0470. You get something super close. I got 0.0465, so just know that you may get something just a little different. You may get the same thing, or you may get just really close. Alright? And so you say, well, how do I get that answer? You're already talking about the answer. Well, here's the z-score. You look up the area that corresponds to that z-score, but since this had greater than in it, you say 1 minus whatever area you get. I got 0.9535. Whenever I subtracted, I got 0.0465. That's why I said I got something just a little different. So that's what I got. On part B, I did notice they changed the x value on me. So that was different from the last problem. I think I may have started out doing it a little wrong and had to go back and redo it because I didn't notice they had changed that x value to 201.20 centimeters. We have the same mean, 202.5, divided by, now since this was 15, that's where the central limit theorem comes in. So I'd still divide by 8, but it's really 8 over the square root of 15. Now, when you work out all of that, you're going to get about a z-score of negative 0.63. If you look that up in your z-score chart, that's going to give you 0.2643, but that's not the answer. Why not? Remember, the greater than was in this problem. So since it said greater than, that tells me I need to say 1 minus that. And I got 0.7357. And that's my answer. Again, look how much I'm off. I'm off like a 2/10,000ths of a place. So it is off just a little bit. Okay. You can see down there the error correction that my answers that I got are actually listed, but it wasn't the one that was given defaultly in the program whenever I went to my test review. Now, remember, the normal distribution can be used. Why? I briefly mentioned it earlier. Either your original set of data is normally distributed, or n is greater than or equal to 30. Well, n is equal to 15 here, but since our original set of data is normally distributed, we can use our normal distribution. Right. Number 39 is very similar to both of those problems. The only difference is, of course, on the first one, it's just like the other three problems I've looked at. You only want the probability for 1. Okay, so you don't really have to do anything different. You don't have any square root of anything in your z-score formula. But when you do B, you do have 441. So you're going to have that to put into your z-score formula in the denominator. You're going to have the square root of 441. Okay. Now, this says at least. I was looking at that in the problem. This says more than. This says at least. More than or at least is going to just mean the same thing for these problems. More than, we're going to have to say 1 minus whenever we get our area. The same on B. At least, we're going to have to say 1 minus when we get our area out of the table. Okay. And then the last problem, which of the following is not a conclusion of the central limit theorem? The distribution of the sample data will approach a normal distribution as the sample size increases. All right, that's not a conclusion of the central limit theorem. Okay, the rest of these are. That one isn't. And that finishes up test 3 review. I know it was kind of long. Make sure that you go back and re-watch problems, and you could even pull the problems up as you're working out the test, and you could watch me work out one like the ones on your test. Take your time. You're not going to have a time limit. Make sure that you don't stress out or anything, and take your time. Hopefully allot yourself at least, I'll say at least 2 or 3 hours to take this test. If you have any questions before you take the test, feel free to email me or call my office, and I will try to get back with you if I'm not there. Have a great evening, and I will see you soon.